Thank you very much to follow us all the week. This is our last day, and this is our last agenda for the event. We will have a presentation made by Michele, Sandro, and Kosuke with advanced topic and recent application about the Quantum Monte Carlo and TurboRVB. Then we will have, as usual, at 10:30 the virtual coffee break. And then we will have the conclusion remarks made by Michele Casula. At the end, during the last part of the day, so during the conclusion remarks, there will be a poll where there are 10 questions that you have to answer. In the end, if you reach the minimum number of correct answer, you will receive a certificate. So now I want to introduce our three speakers. So Kosuke, Sandro, and Michele, as you know already, since you spent a few times this week. And nothing, I want to leave the floor to Michele, that is gonna start, or Sandro. The floor is yours.
Okay. Good morning, everybody. Thanks for being here till the end of the school. It's been quite a marathon, but anyway, so we're going to end today with some applications. So that's will be the first part, and then we'll have the question time, as Jacopo told you, and at the end will be the conclusions with the final remarks. So let me share my screen and open the presentation about applications. So those applications have been done by using the TurboRVB code you've been using during the school. So you will see the capabilities of the code and what you can do with it once you will become an expert user. And I wish you to become an expert user as soon as possible to exploit at most the capabilities and do the nice physics you can do with this code. Yes, so let me find the presentation. Okay. Okay. Right. So I give the outline of this presentation presentation about applications, and so we'll be three of us speaking today for presenting our respective research, and so that's the outline for this lecture. The first point we're going to talk about is concerns the correlation-driven dimerization in graphene. So it's a work Sandro published in, I think, 2 years ago. So there is this archive reference here, but it's published on PRL. So that's the first point. So about graphene, strain graphene, and also topological properties under strain, with phase diagram actually computed by Quantum Monte Carlo, so it's a very high accuracy and high reliability. The second application will be about the hydrogen and the mixture of helium and hydrogen. So how to compute the phase diagrams of solids, of crystals with Quantum Monte Carlo, and in particular in this case it's not about solid crystals, but it's about the melting of the crystal, and so the liquid phase. and the study of the liquid phase under pressure and high temperature. So those are called extreme conditions, which are relevant for not only for condensed matter physics, but also for planetary science, because hydrogen and helium are abundant elements in the universe, and they are basically the major constituents of large planets. And having the knowledge of the phase diagram of these elements will make a better understanding of also the physics taking place in those planets. Right, so so that was the third point about hydrogen and hydrogen mixture. The second point, sorry about that, it's about the hydrogen chain. So the hydrogen chain is a sort of a model system where the hydrogen atoms are aligned on a row, and you'd like to study what are the properties of the system made of hydrogens in a row when you change the distance between hydrogens, the density, if you like, the linear density of hydrogen atoms. And then from hydrogen, we'll move to the spintronics property. The spintronic properties of spin edge states in graphene nanoribbons. So if you cut now a graphene into ribbons, into stripes, then you can have peculiar states at the edge of these stripes, and we're going to see how these edge properties are sensitive to the correlation. Thanks to the Quantum Monte Carlo calculations on a set of molecules which are representatives of these ribbons. After that, we're going to move to the superconductivity in strongly correlated systems, in particular in this class called iron-based superconductors, and we're going to see the pairing function of the iron selenide. So iron-based superconductors is a family of new superconductors discovered in late 2008, and so those have been the subject of many studies, because those are, if you like, a new family beside the well-known cuprates, which are the textbook, if you like, textbook materials for high temperature superconductivity. And then we're gonna see also some applications for proton hopping, proton transfer in water clusters. So the hydrogen bond is one of the most challenging bonds in quantum chemistry, because it's mediated by not only by the chemistry of electrostatic and chemistry of the interaction between the electrons in hydrogen and the electrons of oxygen in case of water, but it's also mediated by nuclear quantum effects. So you have to incorporate both the electronic and the nuclear degrees of freedom to describe properly the proton hopping and also the hydrogen bond. And then there is another point, or a few points, will be presented by Kosuke about the phonons in diamond. I guess, right, Kosuke? Phonon in diamonds. So it's recent applications we have made together, Sandro, Kosuke, and myself. Well, Kosuke, Sandro, and myself in the right proper order, maybe, which is basically we achieved to compute the most accurate phonon spectrum never computed for diamond by basically killing the error bar down to the terahertz range. Okay, so let's start with the Sandro part. I invite Sandro to reach the desk here. And actually, so the order of the points is a little bit misplaced. So we're going to start with the hydrogen chain. And so I give the floor to Sandro, and you can take over.
Okay, thank you.
Oh, I don't know, you can change it.
Okay, can you hear me? So thank you to Michele for the nice introduction. Sorry, now I don't need, since Michele is far enough. And this is the first example where we have shown in a very simple system, but simple but difficult enough to be realistic. What is the difficulty of this system? You have the hydrogen atoms interacting with the full Coulomb interaction, so the thing that is implemented in TurboRVB. And within this Simon's collaboration, we want to show that we don't know the exact solution of this model, of course, and there are several difficulties because we want to do bulk property. So we want to reach the thermodynamic limit. So we have to do several electrons. Nobody knows, as I told you, the exact solution of more than 10 electrons. But we want to show that we can reach a satisfactory accuracy because at the end of the story, the method agree on the bulk, so the thermodynamic limit energy, in a very, very small range of uncertainty. This is a plot done in milliartri per atom, and you see that the most accurate method fall within this uncertainty. And this is very difficult because we work in a finite basis, we have a continuous system, and all the methods work on a finite localized basis of the type that I've described. Is something wrong? No, can continue. And we want also to remove completely, please go ahead. We want to remove completely also the finite size basis error. I have to emphasize that in this collaboration, the method displayed here, you can imagine, PMC and LRDMC are done with the TurboRVB code, and the DMC method is almost the reference method, especially in the large pressure limit. Actually, the story is quite... we have discovered that in this region there was a problem with the standard basis set, and I was discovering it. Well, we have time, so I can also do some story. No? You remember I claim that we have a very good way to control the basis set, and this was really important in this region. And what happens? This calculation was done in the most simple, tool that we have in Turbo. So we do a density functional calculation with the DFT code implemented in Turbo, working with the final basis set, and then we apply the diffusion Monte Carlo. So without optimization of the nodal surface. The reason is that in this system is simple enough that DFT makes a good job for the determinant part. And by doing my DFT, in order to be, I work with a finite basis, I was comparing my energy, DFT energy, with the quantum espresso, and then I discovered that when I was below this region, my energy was completely different from the quantum espresso, and what then I was saying. And this was, and I was getting similar energy of the other benchmark. They didn't notice this. So I went, I just by hand, because as you see, you can use the double zeta basis for the If you use the double zeta or triple zeta or quadruple zeta or quintuple zeta, nothing happens. Your energy will, DFT energy will have nothing to do with the quantum espresso plane wave calculation with large enough cutoff. I don't know, I did 400, 500 Rydberg cutoff. And then just by hand, but maybe my code is wrong. Because after this region, it was essentially superposed. And then I discovered that by decreasing by hand the exponent of the p orbitals, I was getting lower and lower DFT energy. And at some point, by hand, I was able to find a basis that works also in this region. And I said to my collaborator, look, that in this region, you can take your bases that are prepared by the quantum chemistry package, and you can throw in the wastebasket, but you can never reach a reasonable accuracy. And after that, and we did another paper. There was a reason why the basis didn't work, and you can find another paper recently also in the Simon collaboration, because here there is a very, very nice metal insulator transition in which there is a band crossing. And what happened? The band crossing is quite anomalous at large pressure. This is a very interesting model. At the end, we discovered that the pi band becomes very diffuse. So the usual basis set cannot incorporate a very diffuse, very delocalized pi orbitals. And so if you don't decrease the exponent of your basis, you never represent this transition that is due to a band crossing of the pi orbitals when you go to very large pressure. So this is the story, and I want to emphasize another thing. The Simon's collaboration, you know, is a US. I have to do also to advertise my code. So there are several QMC pack, but they cannot have this kind of accuracy with localized basis, since and they use usually plane wave basis, but since all the benchmark was done using a localized basis set, because we want to show that we can actually reach exact result with localized basis set, that's why TurboRVB was chosen for doing this benchmark, and it was very successful. This is also the reason why, I don't know, probably in the future, I will try to put the plane wave basis set also in Turbo. But the point that now that we have solved this problem, the problem is that if we use the plane wave basis, we cannot optimize. So we lose, because the number of parameters, as I told you, if you use a plane wave basis, if you use a localized basis, for instance, you have essentially 10 variational parameters per hydrogen in a triple zeta basis. And then you have to square this number, because you need the math. For the atomic basis, you have 10 elements per atom. If you take a plane wave basis, and 2 orders of magnitude larger. So you cannot do any variational calculation with a plane wave basis. And you have the same accuracy, as I told you, because if you have enough basis, you can reach the accuracy of quantum espresso with 800 Rydberg cutoff. I have checked. Unfortunately, I don't have the plot to show you, but believe me. So basically, with this method, we have state-of-the-art on this system. This system, probably you don't have to believe that for all systems we have such kind of accuracy. The system is particularly simple for diffusion Monte Carlo because it's one-dimensional system, and therefore the nodes are determined only by symmetry, and this is the reason why we don't have to optimize the wave function. The Slater determinant has essentially correct nodes, and we don't have to do any effort. You just push the button and you do your LRDMC calculation. In more realistic material, if you go to 3 dimension, the problem becomes more tough. But anyway, this is in this system we compete with the most accurate technique. How to go to the next slide? Yeah. And this was another challenging application, and still I'm working on this to understand the property of bulk system, so at very high pressure. This is very important to understand big planets like Jupiter, where if you go in close to the core, you reach very, very high pressure. I think the pressure already here is about 300 gigapascal, something that is you cannot reach. You can reach also in the lab with Devil, with some particular experiment, shock waves or diamond. Repeat, tell me, I don't remember, but anyway. But it's very difficult, and in this case, the computer simulation is very important because you can do in silico something that basically is very difficult to do experimentally, to reproduce the properties of our planets that we cannot do the experiment at this kind of pressure. And what is the main point? The astrophysics try to understand the spectrum that you can receive from our planets, and this heavily depends on whether at high pressure the system is metallic or insulator. So you have obviously very completely different response to the light and the emission that you can interpret. So you have to have a model to interpret your data, and if you don't know if the system at this pressure is metallic or insulator, or at what is the pressure where the system becomes metallic, you cannot understand at what part you can draw this, because this is supposed, is believed to be a first order transition, so you have several come si dice, strati, several layers with different behavior in a given planet. The problem concerned very, very light atoms, because you know, most of our galaxy, not only of Jupiter, is done by hydrogen and helium at most. And so what we did was to, well, this is just an explanatory transparencies that I've already said in Word, basically, that you can, these are very extreme conditions that are much better obtained by simulation techniques. And so basically, when you do density functional theory, you try to reproduce experiment. The hope of Monte Carlo simulation is to predict without also DFT, but DFT you never know if your functional is good. You change the functional, you get a different response. So basically, it should be more trustable, especially for this problem when you don't have experiment, basically, and you want to predict the material properties at extreme conditions. This is what we have done with this, yes, this is to show, for instance, the phase diagram. And one of the questions, you take the pure hydrogen and you ask what happens, and you increase the pressure. So the atom becomes closer and closer. And when, so you know, at ambient condition, you have a gas of molecules, because we have seen in the exercise that the hydrogen molecule is very stable, has bond length of 1.4 atomic units. And if you are at ambient condition, the distance between two atoms is several atomic units. So it's much larger than the bond length. But when you squeeze with high pressure, the average distance between the atoms becomes of the order of the atomic distance. I think at 300 gigapascal, you get something of the order 1.3 atomic unit, the average distance of the hydrogen. And in that case, you cannot distinguish a molecule from the atom. And it is believed that when you squeeze enough the system with high pressure, you go from a condition in which you have a gas of molecules that have certainly a gap, because in order to move an electron from one molecule to another, you have to pay the gap that is necessary to break the molecule. But when you have an atomic system where you cannot distinguish the atom from the molecule, you can bring more easily one electron from one side to the other, because you don't have to break the molecule. And what was speculated in the early days of quantum mechanics by Wigner and Etherington, that there should be a metal insulator transition as a function of pressure, even at zero temperature. You see that if you do density functional theory, you get, you take any function. So the first calculation was done by Sandro Scandalo in SISA, was a milestone in that period with density functional theory and PBA. And he reported the transition, a metal insulator transition with this line. But you know, PBA has not the long-range interaction, and there are several ways long-range weak interaction. Van der Waals interaction cannot be dealt with conventional functional in density functional theory. There have been a lot of progress, but this is one of the major deficiencies of density functional. And so what we try empirically to add some correction to the density functional. And you see that these are standard density functional, df1 and df2. You can change completely this phase transition, even by 300 gigapascal. And so you can fit any experiment that they want. Actually, there was a recent experiment 5 years ago that was claiming that the pressure, the transition pressure was here and not here as compared with the previous experiment. And so he chose an appropriate density functional theory, and he got superposition with the theory. So this is, you know, this is the thing that you can do with density functional. If you know the result, you can fit any experiment, at least qualitatively. It's not. But this cannot be done with Monte Carlo. We have to believe always to the method, the variational wave function that has the lowest energy. Not necessarily we get closer to the experiment if we decrease. Probably because not necessarily the Monte Carlo is wrong, but because the experiment is wrong. Indeed, nowadays, it is strongly believed that they characterize the Knudsen, characterize the transition not in the correct way by looking some kind of crossover behavior. And so that was the reason why it was so far. But I have to say, At present, there are two different Monte Carlo simulations. I don't know if you have these slides. One given by the TurboRVB group, by myself, Guglielmo Cazzola, that was a PhD student, that now agreed after, after a long debate and discussion that the phase transition, this kind of phase transition should occur a little bit on the right with respect.
The next one, Sandra.
The next one.
Two slides. Yes, 2 slides.
This was, yes, this is the way to identify the transition. This is the first order transition. You compute the pressure as a function of the average distance between the atoms. As I told you, is around 1.3 at 300 gigapascal. And you find, when you find a plateau, this is because you have a first order transition, a change of volume at the same pressure, and you find a plateau of the pressure as a function of volume. This is in the previous, this is the, in this picture is emphasized that, I mean, Quantum Monte Carlo doing this kind of realistic calculation is just begin. At the beginning, we did the calculation with a small basis set, and we get results more consistent with the Knudsen experiment to a very large pressure. After we did, but we were not in agreement with the separately group, but after that we discovered there was a large error in our basis. We increased the basis, and as I told you, using the basis that is now the standard basis that worked so well in this benchmark calculation. So this work was done before this benchmark calculation. We got much different pressure, so much lower transition pressure. And therefore, our results are more or less in agreement with another simulation done by Monte Carlo with a different method of sampling, with a different wave function, probably even slightly better in accuracy in variational energy, but we more or less agree on this transition pressure. Oh, let me show you, it's reported here. So this is the result of the separately group. The first author is Pier Leoni, and this is now our result that is almost consistent with the separately group, and is, as I told you, is well, not significantly different from what you can get by density functional theory using the PBA approximation. Whereas DF1 and DF2 are, I think, out of the blue. So there is still some problem out. Of course, Monte Carlo does not have to include any other ingredient. Directly, we have the van der Waals interaction, even at the variational level, because it's enough to have a just of 3 body, not even 4 body, to obtain the van der Waals, the weak van der Waals interaction correctly. This is obtained by optimization. And therefore, we are pretty sure that, I mean, we are now doing another work, maybe more accurate than this, and that will not change much this transition line. So at the end, the purpose, the target, I mean, this is a very delicate transition, as you can see, and the target of computer simulation is to have this transition accurate within 5 gigapascal, I think is the target. And this still, even though we have quite enough accuracy between 2 different Monte Carlo methods, I think nobody can say now that we have an accuracy of 5 gigapascal. So there is still some work, improve the wave function, improve the method, and reach, in principle, this target accuracy. let's go to the next slide. I'm going too slow or too fast? It's okay. We shift, no, I don't know, we shift. Well, the quantum effect, you can add quantum effect on the nuclei and you shift, and this is the more realistic calculation. And this is shift a little bit. So for some reason, when you put the quantum effect, you get closer to the original PBA calculation that was done without quantum effect. So it's with some anomalous cancellation of error, the PBA without quantum effect is close to the experimental result for the wrong reason. Somehow. Another, unfortunately, there is not the system that we are talking about, probably here. So we want to understand the property of graphene. Graphene is a semi-metal. The particle you are, well, this is not the right picture because it's already deformed, the graphene, but you can understand that this is an honeycomb lattice. And what, so somehow at zero temperature should have finite conductivity because it's a semi-metal. And instead at finite temperature should have the semiconductor behavior. And the thing is that but we know that if we increase the value of the interaction, so, you know, as I have done in the first, I think, lecture, I've shown the benzene molecule, and also in the graphene there is only one valence electron per carbon site. So you have one valence electron. And you are in the condition of strong correlation because the two valence electrons on the same carbon site are unhappy because they will pay a strong Coulomb repulsion. But the Coulomb repulsion is not enough strong to have an insulator. You know that if you increase the value of the U of the so-called Coulomb short range, so how much we pay in energy when two valence electrons are on the same carbon site, if this U is very large, this is a strongly correlated phenomenon. Most of you that work in strong correlation knows. If you don't know, I just tell you, it's a fact. If you increase in a system that has one electron per carbon site, that according to band theory should be a metal or a semi-metal, but if you increase the value of the on-site interaction, this will have a transition to a so-called Mott insulator. And how to increase the insulator behavior of this system? That this was an academic, but not so much academic, because experimentalists can apply negative pressure in some sense. So they can stress, they can dilatate, enlarge the system by for instance, with the scanning tunneling microscope, they can take one part of the system and dilatate, so they enlarge this system, and they can do experiment under stress, under this stress, so that the average distance between two carbon atoms becomes larger and larger. And what happened when the distance, average distance between the carbon atom becomes larger and larger? The value of the Coulomb interaction remained the same, because this is a local property that is the characteristic of an atom. But the probability to go from one carbon, for the valence electron, to go from one carbon atom to the nearest neighbor atom becomes exponentially lower. So you basically, when you squeeze, so when you dilatate, enlarge your system, you effectively, you are trying to see what happens when you increase U over T. And what was the funny phenomenon that we have found? That we found an insulator, but was rather unexpectedly, because we would have expected, like in the hydrogen chain, if you increase enough the system, it displays antiferromagnetic correlation. We would have expected antiferromagnetic correlation. This is the calculation done from DFT that actually, I think, reported that the enthalpy energy of the antiferromagnetic phase should be smaller, lower, so more stable when I increase U over T of a dimerized phase. A dimerized phase is obtained in the picture that I have shown later. So when you apply uniform stress, instead of getting uniform dilatation of the hexagon, you form a bond that are more close than the other, for instance. These are larger distance. This is obtained by full relaxation. I will show the film in a moment, using TurboRVB, instead of obtaining an antiferromagnetic phase. Well, these are quite technical. So if you want, this UB means upper bound. We have an upper bound of this enthalpy that has lower energy that, well, maybe you don't have to see because we can compute directly the energy with larger error bar. So probably we not have. So this is an upper bound of the dimerized phase, and you see that is much lower than the DMC. So we did also the LR-DMC calculation. Of the corresponding phase antiferromagnetic, that is the green, that is almost, you see almost an indistinguishable gain with respect to the undistorted solution. So I think we have also the DMC, which is obviously respect the upper bound, is even lower. So the robust effect that we see that instead of having an antiferromagnetic insulator, we have a very nice dimerized state. So how to show this? Well, let me emphasize that a dimerized state, so when you have a valence bond, what does it mean? In the picture of the benzene that we have shown, we have, this was one of the Kekulé structure that you have to sum with the other one to get a fully isotropic molecule, because the molecule, we know, does not break any rotation. But in this case, we break the symmetry. So there are valence bond configuration that have lower energy. But this is also a non-trivial state, because in order to build a wave function that is made of 3 valence bonds, like that, each valence bond is an Heitler-London combination, you know, in order to not to have the atomic contribution, otherwise, as I emphasized, with a single determinant you cannot do. And so you need 2 determinants for each single bond. So only for having a dimerized, to represent a dimerized state for the single hexagon, you need 8 determinants. So this is, if you want, a highly correlated system, even if you don't have the resonant valence bond. And you can imagine what happened to represent this kind of state in a graphene, where we have, in principle, an infinite number of hexagons. And this is indeed possible, and actually we have shown that only thanks to the optimization of the antisymmetrized geminal product, you can represent this non-trivial correlated phase of matter with the single determinant updates. Now, in Monte Carlo, thanks to the geminal, we can reproduce all valence bond that we have. If we put the right projection, we can eliminate the possibility that this valence bond is occupied 2 times with 4 electrons. So we need also the Jastrow. But if you put optimize together the Jastrow and the geminal part, you can represent also this non-trivial phase of matter. So let me show now some funny film. So this is how the optimization evolve, I think. No, this is nothing. No, this is probably. You see that there are 2 kinds of phases. One that is obtained when basically the system wants to break, when we have this dilatation is too large, and you have basically isolated hexagon that are far apart. And in this case, you have already. But the interesting thing that I don't, the film was not funny enough. You have not. So basically, this is the final configuration starting from the initial symmetric one, and you find this dimerized state that is called of the calculate type. Sorry, probably I've taken too much time. This kind of K-Goulet phase is also realized in lattice model, but you have to put a rather non-trivial and long-range interaction. And I have to say, if you take the standard Hubbard model on the Heinegon lattice and you increase U, you don't find this calculate phase. So this suggests you that to have a realistic calculation sometimes provide you effects that you cannot understand easily with lattice model calculation. And I think I have finished, and you, Michele, should go to the application of Oligon.
Yeah, okay. So now let's go from the graphene sheet strained to the nanoribbons of graphene. So if you cut the graphene sheet, you can get different kind of nanoribbons, and they can differ from the width, of course, but also for the edge shape. And so this study is the one I'm going to present today, is about the shape where you have a zigzag profile. Okay, you can see here from this set of molecules, and so those molecules can be seen as a finite length wire, while you don't have just the cutting the graphene on the side, but also the cutting at the start of the end. So you get basically a finite wire, and so this basically it's a molecular counterpart of the graphene nanoribbons. And we started studying these molecules because those are easier to study, of course, than the infinite wire. While retaining the main physics, we believe, of the wire. And so those molecules, by the way, are interesting not only because they can be seen as zero-dimensional graphene nanoribbons, but also because their chemistry is extremely rich, and their functionalization, for instance, is crucial in many many fields of chemistry, ranging from hydrocarbons with properties, with pigment properties. So dyes are made of this kind, or functionalization of these kind of molecules, for instance. So pigments are made, constructed based on this skeleton, if you like. So the understanding of these molecules is fundamental, not only for solid state physics, if you like, but also for quantum chemistry in general. And we studied the full series of these acids. So that's the family we're talking about, from the anthracene up to the non-acene. So as you can see here, they differ by the number of benzene rings. Okay, and as you increase the length of these molecules, you increase also their reactivity with the environment. And so while anthracene can be stable, is found stable in normal environment, larger and larger molecules like heptacene, octacene, and even nonacene are much less stable, and they can be synthesized only in some metrics, some inert metrics like noble gas. Okay, so what is the challenge behind these molecules? One of the challenges, because there are several challenges to understand these molecules, is the nature of the ground state. Okay, so the nature of the lowest energy state. If you compute the ground state by using DFT, density functional theory, using the B3-leap functional, you get an instability towards what is called unrestricted phase, unrestricted state. And this unrestricted state is characterized by the localization of electrons at the edge of these molecules. And so you have the two homo orbitals, so highest occupied molecular orbital, one localized at the left-hand side of the molecule and the other at the right-hand side. And these two orbitals are occupied just by one electron, so they have filled. One electron up from the left, down for the right, or vice versa. So that's why they're called open shell, because the filling of the molecule is such that both edges are just half filled, and both edges are basically lying at the same energy. So you have a ground state with open states, open shells. And this could explain partially the higher activity of this molecule, because of course, if you have an open shell, this feature makes the molecule prone to form chemical bonds with the surroundings. So is it the right ground state? So that's the solution of DFT using this function, which is a hybrid function. So it's a hybrid function. It means that the function which includes both a PBE component built on the electron gas, as I told you, the first lecture, the physics of the electron gas, the homogeneous electron gas, and also a component which is made by a Hartree-Fock exchange part. Is it just a feature of the functional, or something we can trust? That's the usual question when you have DFT. I mean, the DFT can provide you different results, and you should, know what are the validity of the functionals in different situations to trust these results. In this case, the system is strongly correlated, and so it's worth studying it by Quantum Monte Carlo. So graphene nanoribbons are the focus of many research, and I just put here a paper published on Nature in 2016, where they claim to have been able to cut the graphene sheet into ribbons, and you can see here that according to the angle of cutting, you can have armchair profile and the zigzag. So as I told you, zigzag is our topic today. And so this is also again, it's the challenge to synthesize those systems because they're very unstable and chemically reactive. But now you can have examples even in solid states, apparently, according to this experiment. So those are the questions we are addressing in this study. So what is the role of dimensionality and quantum fluctuations to set the ground state properties, because these systems are 1D or even 0D for the molecules. So quantum fluctuations are supposed to play a very important role to stabilize the properties of the ground state. And what is the magnetic state? What is the magnetism of this molecule? Is the magnetism provided by the open shell with up-down and down-up correlations at the edge, or there is something different going on? And if the spin polarization survives beyond the DFT approximation, so it survives upon correlation. So all these questions are addressed in the work I've done a couple of years ago. It's been published in 2018, I think. So, so we have seen, Sandro has shown you the AGP wave function, right? And so there is a particular situation where the AGP wave function can indeed represent this open shell situation, where you have this correlation between up-down electron sitting at the right-left edge with the down-up sitting at these edges. So in that case, in a case of an open shell singlet, you have the lambda expansion of your geminal for the HOMO orbitals equal to the lambda, the strength of the geminal expansion for the LUMO orbitals. So in that case, if lambda HOMO equal to lambda LUMO, you have exactly the situation of two perfectly degenerate states at the Fermi level, HOMO LUMO equally filled and half filled in the case of these ascenes. So this open shell singlet configuration, the signature of this open shell singlet configuration is translated in the AGP language by having the amplitude of the lambda parameters equal for the HOMO and LUMO orbitals. And so in this left-hand side plot, the open shell singlet limit in the AGP wave function, just of AGP, is represented by the dashed line at the bottom here. And so I represent then two types of wave functions, the J double determinant, so where I construct the AGP such that it represents just two determinants, the leading determinants are just two, and instead the RVB, where I switch on all possible lambda IJ couplings in the geminal such that I create really the resonating valence bond physics. And you can see that the JDD, if you constrain the expansion of the AGP such that you have two leading determinants in the geminal expansion, this JDD tends to the open shell singlet limit at large molecules. So on the x-axis, I report the number of rings in this ascene series. While in the RVB, when I project the RVB into the molecular orbital representation, the coefficients HOMO LUMO around the Fermi level are such that the LUMO part is somehow much smaller than the HOMO part. So you have all the resonances above, beyond the R3-Fock solution are equally shared at a much wider range of energies, such that the first unoccupied state in R3-Fock is not that important, okay? Not because the system is single determinant, but because you switch on correlations at much higher energy range. So you have resonances with higher energy orbitals as well. And so that's the RVB, if you like, feature of if you just restrict your attention to the first excited state, if you like, in the R3-Fock mean-field representation. And so the actual ground state is a much more complex state because it's a resonance between many states, okay? Many single particle states. Now, if you now try to understand what is the filling of the HOMO and LUMO orbitals, as I told you, the open shell singlet is the case where you have half filled on both sides of the molecule, okay? Of half filled orbitals on both sides of the molecule, so the HOMO and LUMO are equally populated. And so if the HOMO and LUMO are equally populated, the difference between these two occupations should be 0. So a signature of the pure open shell singlet in this representation, where I plot on the y-axis the difference between the populations of the HOMO and LUMO orbitals, is a situation where this difference is 0. So it's when these curves hit the x-axis, it means that you reach the perfect open shell singlet regime. And so I plot here all publications, all papers on this problem. So first of all, you see how many works have been done on this. So it's a widely studied problem in quantum chemistry, and you see the varieties of results you get according to the method. So it's kind of interesting, and it illustrates, if you like, the difficulty of getting meaningful results or trustable results on this problem, which is strongly correlated, and you have you can get basically everything here in this range. So all methods span this range, and the question is, what is the best one among all these methods? Okay, so we know that that Quantum Monte Carlo is the best one, at least in this regime, because it's the one which includes the most of the correlation. And but again, within QMC, we can play with the wave function, so we can control, if you like, the physics we put in the ground state, and so you have different flavors here, different quantum chemistry methods plotted here, ranging from unrestricted R3-Fock, which is this pink here. The unrestricted R3-Fock basically exacerbates the broken symmetry solution. So you have clearly, it's the most if you like, prone to get into this open shell singlet regime. And then you have more and more refined methods which somehow delay the occurrence of the open shell singlet regime, where you should go down at hit the 0, the x-axis here. It's nice to see that our JDD representation. So when your AGP is basically can be expressed as two determinants, the resonance between two determinants. It's nice to see that these the curve of the different populations between HOMO and LUMO as a function of the number of rings follows quite closely the RPA result. RPA is already an advanced method, okay, because you include diagrams at all order in the bubble form. So so it's a very advanced method, and it follows quite closely the JDD. But if you improve further by using the full RVB power, you can see that the RVB is the one which delays at most the occurrence of the open shell singlet regime, and actually in this window from 1 to 14, this open shell regime is never reached, and you are very far from it. And that's basically, again, this, by getting rid of all the methods but Quantum Monte Carlo, you get this exactly what I told you. The RVB basically is the most correlated one, delays enormously the occurrence of the instability, the open shell signal instability. That was for me a very nice result, because it tells you somehow that the correlation prevents the occurrence of the open shell singlet, at least in molecules whose length is accessible experimentally, because if you go beyond 14 rings, you're talking about academic problem, because 14 rings is never found in nature actually. So inaccessible as seen molecules, the open shell singlet is very far from the true ground state. Now, it's interesting also from the AGP wave function, Sandro introduced you the second day. It's interesting to study also actually the values of the lambda IJ coupling. So these lambda IJ couplings are not just parameters which optimize the energy, but they carry, they bring about some physical information, okay? And so if you plot, for instance, the lambda IJ in the RVB representation for these molecules as a function of the carbon-carbon distance, you can see that there is a long range, it's a power law decay of these lambda IJ parameters. So the RVB correlations are long range in these molecules, in these aromatic molecules. And you can see the nice difference also between two branches. The sigma branch, so the orbitals lying on the plane, on the molecular plane, and the pi branch, so the lambda IJ connecting PZ orbitals, which are the lowest energy orbitals in these molecules. So the pi branch decays even more slowly than the sigma branch, which lies on plane. I think I got a question. Let me see. No. Okay. Okay. So yes. So the RVB physics enhances aromaticity and suppresses the edge localization, which is basically at the heart of the open shell singlet physics. Yes, so this is the reference for this work. Yeah, so there is this the paper, the latest paper I was mentioned to you, the JCP in 2018. Okay, so and this has been the subject of a PhD thesis of one of my students. Okay, so yes, so let's so if you like, just to conclude this, put this in a wider perspective. So the fact that we didn't find any sort of phase transition or localization in this system is also in agreement with the Mermin-Wagner theorem, where you believe that in 1D you don't have phase transitions in general, because charge fluctuations, spin fluctuations are very strong. So that was also reassuring from this viewpoint. Okay, so anyway, let's move on, and so let's change our topic. It's another topic very far from the previous one, but very important as well. So a big chunk of the condensed matter community studies, I would say, very, very intensively strongly correlated compounds with the goal of understanding high temperature superconductivity. Okay, so so high temperature superconductivity is a property of some materials which show superconducting state at much higher temperature than the one predicted based on the regular BCS theory. So if you apply the BCS theory in these materials, you would predict a much lower critical temperature for superconductivity. And you know, the BCS theory is the one which relies upon the coupling between electron and phonons to to open a superconducting gap, so to make the form, to form Cooper pairs in the material, and such that these Cooper pairs can superconduct. So if you apply BCS theory, you wouldn't get the right critical temperature. You would get a much lower critical temperature than one measured in experiments, and so the first members of this family of high temperature superconductors has been discovered in '86, and those are the cuprates. And since then, a lot of physicists spend their life and their days and nights to understand the origin of this phenomenon. And it's believed that the way to explain it is somehow related to the strong correlation which acts in these systems. So because you see that these systems present phases which arise only if you assume strongly interacting electrons and localized electrons due to strong correlation. And so, apart from the superconductivity, then this strong correlation leads to complex phase diagrams. So these systems are very complex to study because they don't not only show the superconducting regions, and that's highlighted here in this plot by this pink dome here, as a function of doping, for instance, and temperature, but they present also competing phases, and all these phases are somehow obtained by the subtle competition between correlation and delocalization and magnetic fluctuation. So you have a lot of processes going on in these systems, and those are driven by, generally speaking, by electron correlation. But the electron correlation makes this system extremely rich and extremely also hard to understand. One of the common features of their phase diagram is not only the presence of the superconducting dome, but also the presence of spin density waves or insulating antiferromagnetic states. And this is the example of a new family of high TC superconductors. It's iron-based superconductors made of planes, layers of iron with pnictogen or chalcogen, and then these layers are usually interspaced by charge reservoirs like barium, for instance, which provides electrons or holes in the system. And indeed, this charge reservoir is fundamental to tune the doping of this system, because usually the superconductivity arises at finite doping. So you have to dope the system to make the Cooper pair superconducting. So the discovery in 2008 of iron-based superconductors was an excitement because it was a new family of systems beside the cuprates to share the property of having high TC. Again, even in this system, electron-phonon coupling could not explain the high critical temperature. And so these systems represent a new avenue to study this phenomenon, a new playground, if you like. Although these systems are possibly even more complex than the cuprates, because they have clearly a multi-band physics. So it's not, I mean, if you like, the electronic structure, the band structure of cuprates can be explained the simplest possible model by a single band, while although the single band is hybridized between the D and P P states. But anyway, in these pnictides, or hydrogen, in more general, hydrogen-based superconductors, it's clear that a multi-band physics takes place. And so you have to describe the electronic structure more accurately because you should include all these ingredients to get a reliable description of the materials. At this point, we said, okay, look, I mean, now we have the Quantum Monte Carlo method, which is much better. We believe it's much better than DFT, or at least it's much better in these regimes where strong correlation plays an important role. What about applying Quantum Monte Carlo to these materials? And so we did this, and we chose a particular compound, still iron-based, but this is basically it's iron chalcogenide. Okay, so it's iron selenide. And the reason why we chose this compound is because it's much the unit cell is much simpler than, for instance, this one. So you have less atoms in the unit cell, and so one of the, if you like, the weaknesses of Quantum Monte Carlo, which require an accurate finite scale extrapolation, can be somehow is milder, gets milder because the system, the unit cell, is simpler. So we took this, and actually this is also a very peculiar member of the iron-based superconductors because you don't have actually spin long-range order at ambient conditions, at variance with the other members, although you have structural distortion, which can suggest that spin fluctuations break the tetragonal order, and they make the system enter into the orthorhombic distortion. So something I didn't tell you yet is that indeed it's not only the electronic degrees of freedom which matter here, but also the structural distortion is sort of a signature of what's happening at the electronic level, and there is the interplay between geometry and electronic structure to set the final properties of the material. So that's another layer of complexity to be added to the full situation. And that's a phase diagram of our compound. So that's a function of pressure, not a function of doping. So there is no clear way of doping it through a reservoir, because there is no charge reservoir here. Okay, there is no intermediate layer which acts as a reservoir. So you have to really chemically substitute the active layer, if you like, to dope it. But this will introduce, of course, several issues related to the disorder you have by chemically substituting selenium, for instance. So that's not a proper way to go. And a way to tune the properties is by using another knob. Is not the doping, but is a pressure. And so if you compress the system now from 0 gigapascal ambient conditions up to, for instance, 4, 9 gigapascal, even 10, so you see that the superconducting critical temperature will raise up, will go up till the optimal pressure, about 9 gigapascal, where the temperature, the critical temperature is about 40 Kelvin, okay? So here I can tell you that this compound has been also used as a layer on the top of substrates, and the layer, apparently the single layer of few layers system show even larger critical temperature. So that's also a way to improve, to increase the critical temperature. And so we have a sizable gap here, a sizable critical temperature, and we'd like to study the physical properties by Quantum Monte Carlo. Yes, so that's basically the optimal pressure for the critical temperature. We have a TC of about 40, as I told you, 40 Kelvin, and published in several papers. The first one is the Nature Materials of 2009. Okay, so we can ask several questions also for this material. What is the origin of the superconducting gap? What is the underlying electron pairing symmetry? What is the pairing mechanism? And can we predict these properties from first principles? Okay, because there are several attempts to study superconductivity in these materials, but many of them rely on some parameterization of effective Hamiltonians with empirical parameters, and so by doing that you lose the if you like capabilities of being predictive, which is one of the interests of doing these kind of calculations. And so we studied this supercell made of 4x4 irons, so iron atoms. So you have 16 iron atoms with selenium alternating up and down. So it's single layer. So we took just one of the layers with periodic boundary conditions to replicate the layers in the layer in the z direction. It's also to replicate the pattern, the 4x4 pattern also in the x and y directions. So so we had a system with, this, as I told you, 16 iron atoms, 6 selenium atoms, so with 352 electrons, and so we got a wave function to be optimized with 10,000 variational parameters. So that was, you know, a kind of a challenging system, even for the computational viewpoint. And that has been done actually before the advent of GPUs. So, at least before the latest implementation of GPUs. So, what are the active orbitals at the Fermi level? So those are mainly d orbitals, although these d orbitals are strongly hybridized with the ligands, the p ligands orbitals as well. So the p orbitals are centered around the selenium atoms, and the d orbitals are those centered on the iron atoms, okay? And so these, the d orbitals, as I told you the first lecture, are strongly correlated because they are localized, and electrons living in them, they feel this localization, and so they feel also a quite sizable Coulomb repulsion. So if you restrict now your AGP, okay, so you take the AGP out, so we optimized the JAGP wave function, okay, in the restricted sense. So it was AGPS in the language of Kozuke and coworkers. So it's AGP singlet, symmetric, under permutation of two coordinates. And so if you restrict now this AGP and you expand the AGP over the active orbitals at the Fermi level, so the d orbitals, you can separate the AGP part into different sectors. In particular, 4 sectors. The sector coupling even orbitals, and by even orbitals I mean those d orbitals which are even through reflection, even by reflection through the xy plane. Okay, so the even orbitals are shown here. So the xy, x square minus y square, and the z square orbitals. Okay. While the odd orbitals have odd parity, and the odd parity is the one by reflection through the always through the xy plane, and you can see these 2 orbitals here. So they change sign by crossing the xy plane. So if you now split the pairing function into the function which couples even electrons, so electrons living in even parity orbitals, odd, which is the bottom here, even odd and odd even, you can have 4 channels channels of attraction in the language of superconducting Cooper pairs. And so now, now we've been able to plot we've been able to plot the pairing function in the real space, okay, in the real space in the unit cell. By assuming that in this pairing function, which is really describes the Cooper pair, so the attraction between an up and down electron in the singlet state, by assuming that one electron stays at the center of the supercell here, and the other one is roaming around, okay? And so the other one, by roaming, by moving around, can probe the sign structure, the symmetry of the pairing function, all right? And so what we discovered is that that the odd and even channels of the pairing function have an S-wave symmetry, because if you turn around the electron sitting at the center of the unit cell, the other electron doesn't change. I mean, the other electron feels order parameter which doesn't change sign. Okay, and so that's an S-wave symmetry at variance with the even odd and odd even channel, where the other electron, the one which is turning around the center one, feels a sign change of the odd parameter, and you have lobes. Okay, so because now I should explain to you that I mean, those may be self-explanatory, but it's better to be clear. So the red and blue lobes represent positive and negative regions of the other parameter. Okay, and so that was, at my knowledge, the first time a pairing function was sort of was represented from first principles in this class of materials. So that's the first ab initio picture of a pairing function starting from a full ab initio model without any empirical parameters. And actually, we can make some link with the STM experiments on these compounds. So the STM, they tried with STM to see what was the order parameter of this superconducting state, and they found this C2 symmetry breaking. They made a big buzz about this, and published it on Science. But at the end of the story, one can reproduce very nicely the same shape, this hourglass shape tilted by 45 degrees, using our wave function representation, and assuming that the STM is sensitive to the AGP amplitude, an assumption which is can be justified. Maybe Sandro has a stronger argument to justify this, but anyway, if you make the assumption that the STM is sensitive to the AGP amplitude, you find a beautiful correspondence between the shape, the hourglass shape found with our full AGP. Now, this full AGP contains all channels, even, odd, even, and even odd. So these, if you take the full one, of course, you break the point group symmetry of each channel, and so you have a mixture of S and D waves, and the mixture of S D waves makes this symmetry breaking found in the Science paper. Okay, and so what is the reason of this? Is that the reason is that at this a height where you cut the AGP, it's not exactly on the plane of irons. So you cut this a little bit above the iron plane. You are sensitive to the symmetry breaking provided by the alternating selenium atoms, which are basically alternating up and down in a checkerboard way. So you are sensitive to the selenium atom sitting at the center of these cubes, of these squares, which carry some weight of the AGP function. Right. So well, I'm gonna conclude this part because it's time for the break by saying that with the amplitude of the AGP, then the JGP, then you can actually infer the strength of the Cooper attraction and also the condensation energy. So this is very delicate quantity, because in principle the condensation energy is obtained only in the thermodynamic limit, and so something for the time being, so 10 years ago, it was, yes, 9 years ago, it was hard to achieve. Now, with the recent improvements in the code, I think one can afford also the extrapolation thermodynamic limit of the full system. But at the time, we were not able to reach the thermodynamic limit, and that was also the main criticism of the referee. We basically killed our paper. But in any case, so if you just take the amplitude of the AGP at this 4x4 plaquette, you can estimate the gap of the AGP gap, the BCS gap, if you like, converted into the weak coupling theory. And then you can make the connection with critical temperature. And so what we found was kind of surprising, that we were very close to estimate ab initio the critical temperature. Now we should be taken now with all the caution of the caution necessary in this case, because of course in case of strong correlation, the relation between condensation energy and KBTC is not the one of BCS. So it's not, there is no clear multiplicative scaling factor between the two, but the order of magnitude is the right one. Okay, so that's the message, that the order of magnitude of our AGP amplitude for the part which is beyond the Fock, so it's the difference between the AGP, the full AGP and the one, the Fock one, gave basically the right order of magnitude for the gap found in experiment, the temperature measured in experiment. Yeah, so that's the list of results. So that was the first initial calculation of the pairing function. We got this interesting superposition of S and DXY channels for the Cooper pairs, and there was a consistency between this STM experiment and our image, theoretical image of the parameter. And then we have a meaningful estimate of TC from first principles, so with meaningful in quote marks. Okay, so I think I'm done with this. It's time to stop here because it's time for the break, and we can resume afterwards. So I still have some topic. Yes, so I have another topic which is basically the dynamics we implemented thanks to the ionic forces, and then this will be a nice introduction also for the work by Kosuke, where now the forces are also used to compute phonons in materials like diamond. Okay, so I'll stop here and I'll for the break. Right, so let me finish my presentation, and then also there is also Kosuke Nakano, who's going to present the latest results on the phonon calculations in crystals. Okay, so another application which is very important, and it exploits at most the capabilities of our TurboRVB code, is the hydrogen bond study in water and water clusters. So a hydrogen bond, as I told you, is a challenging bond because it involves not only electronic properties. The stability doesn't come only from the electronic side, but it comes also from the nuclear quantum effects, which must be included to properly describe this physics. So, and it's also related to the proton hopping, so that the property of proton to hop from one molecule to one molecule to the next one, such that you have a conductivity and ion conductivity mediated by quantum nuclear effects. And so proton, the structure of proton proton hopping and general structure of hydrogen bond in water clusters has been the focus, the topic of many experimental studies as well, where now the privileged experimental probe is infrared spectroscopy, because with infrared spectroscopy you can measure, you can access the vibrational properties of the molecule, and the vibrational properties of the molecule, some features are hallmarks of the physics of hydrogen bond and proton dynamics in particular. So, so you see here that the focus is more on the vibrational properties of these structures, and vibrational properties are strongly intimately related to the underlying electronic structure. Okay, that's why to get phonons, as Kozuke will explain to you later on, and also dynamics of the system, you have to have good ionic forces. And these good ionic forces are determined when you solve properly the electronic problem. So we developed an accurate and reliable framework to study the impact of quantum nuclear effects in proton transfer at finite temperature. And so we put basically three main ingredients together in our TurboRVB code. The first one is the very accurate treatment of the electronic part. This first point, and this is done with the QMC wave function at the variational level. We included the thermal effects in the dynamics using a Langevin thermostat at finite temperature, which is hard-coded in TurboRVB as well. And then we propagate the equation of motions for quantum nuclei using a path integral representation of the nuclei. And so we combine path integral with Langevin dynamics. And this QMC driven because the forces which drive these dynamics are computed at the QMC level. So all these steps are included in TurboRVB. TurboRVB is not only, just to highlight the fact that TurboRVB is not just a code to compute electronic properties, but it has also very interesting features to run molecular dynamics calculations. So if you focus on this dimer, so it's a water dimer mediated by the proton in the middle, this is called Zundel ion, Zundel complex. You see that there are basically two regimes in this molecule, which these regimes are depend on the distance between the two water molecules. So if the water molecules are far apart, the hydrogen in the middle, the proton in the middle, will stay either on the left-hand side or on the right-hand side. Okay, so the proton will be localized on one or two molecules. While if you compress the two molecules, you bring them together below a certain distance, a critical, I would say critical, so to speak, distance, the proton is no longer localized to one or two molecules, but is basically lies in the middle, is fully shared, completely shared, equally shared, I would say, between the two molecules. And that's basically the diagram here. That's the distance between O1, O2, the two water molecules. And if you go below a certain distance, you have above this certain distance, the proton is localized, and then you have either left on right or right localization. They have two branches. And below a certain distance, a critical distance, the proton is equally shared, and then you have just one single branch in this representation. So the position where this happens, where the distance, the critical distance below which the proton is equally shared, strongly depends on the method you use. And so that's another place where, if you like, a very high treatment of electron correlation is important to describe properly the dynamics of the system. And our QMC results are in good agreement with the couple cluster single double parenthesis triple level of theory, because you can see that our geometries, basically the VMC geometries lie on the top of the pink squares, which are a couple cluster SDT obtained. So just a short slide, theory slide about how we compute the Langevin dynamics. So the potential energy surface is computed at quantum Monte Carlo level, and the forces as well. So those are really, quantum expectation values computed in the way we have seen together in the first day with the Metropolis algorithm, and in the yesterday actually with Sandro, who explained to you how to compute forces, nuclear forces with finite variance in quantum Monte Carlo. So once you have forces from quantum Monte Carlo calculations, you can plug the forces into this set of equations for nuclear dynamics. So now we separate electron dynamics from nuclear dynamics. So we have two dynamics evolving at the same time in the system. Okay, so it's a coupled, if you like, dynamics. Where now these P are momenta, nuclear momenta, and Q nuclear coordinates. And that's a set of equations which tells you that our dynamics is damped by a friction gamma, and this friction is determined according to the generalized fluctuation dissipation theorem to thermalize the system properly at the target temperature. And we exploit here the quantum Monte Carlo noise of the forces to adjust the noise such that the dynamics, the nuclear dynamics is equilibrated at the right temperature. So somehow we exploit the intrinsic noise to thermalize the system in a controlled way. And that's an idea of Sandro and Claudio Tacalite publishing the first attempt of exploiting the quantum Monte Carlo force noise for the forces in this paper, PRL 2007, published by Sandro and Claudio Tacalite. So we extended the previous formalism to the quantum nuclei by exploiting the quantum to classical isomorphism, where now the nucleus is not represented by a point-like, it's not a point-like particle, but it acquires a finite extension, a finite spatial extension through the path integral, which is a polymer in this quantum to classical mapping. So basically, we have a set of polymers evolving in time and interacting each other through the interaction provided by the potential energy surface. And so that's basically a representation. Those are the centroids moving at 300 Kelvin for the Zundel complex, and these molecules are moved by quantum Monte Carlo forces. And so then we can compute properties at the nuclear level, so like pair distribution functions like GOH or GOO, telling how the two oxygens are moving in the relative motion, or how the proton in the middle is moving with respect to one and two oxygens. So that's you have the pair correlation functions, pair distribution functions for OH and OO published printed here. And so this is very interesting system because it's a reference system. So it's a Drosophila system for all quantum nuclear dynamics, because it's small, so it's not challenging in terms of computational difficulty. It's challenging in terms of features, because you have to include quantum nuclear effects at the full level. Okay, so but it's a benchmark system because it can be studied by many different methods at a very high level. In particular, we have a very accurate parametrized potential energy surface, parameterized at the couple cluster SDT level. So we can compare, if you like, exact results with our quantum Monte Carlo results. And what we can see is that the comparison is very good from the difference between the black and the curve from the benchmark result and our variation of Monte Carlo results, our Langevin dynamics driven by variation of Monte Carlo. And so we validated this approach in this benchmark system. That was a validation, okay? And so you can see that the quantum effects are predominant here. They are extremely important. And you can see the difference between classical distribution functions in red and, sorry, you can see the difference between classical distribution functions at the left-hand side against the quantum distribution functions at the right-hand side at different temperature, okay? And so you can see that classically speaking, temperature has a tremendous effect on the distribution function, while if you take the system at the quantum level, for quantum nuclei, temperature has a much milder effect because quantum fluctuations prevail over thermal fluctuations. And so this was the first brick of the story. Then we're gonna use this system in this method is much more challenging systems, and we are up to publish a work with a protonate water hexamer, where now instead of 2 molecules we have 6 molecules, and it's already a system where a couple cluster is at the edge of the doability in terms of CPU time and CPU cost. So I leave the floor to Kosuke. Actually, yes, I should actually put on your presentation. Sorry, Kosuke. I'm gonna do that. Okay. Okay. All right. I think you're ready to go.
Okay, hi everyone. Can you hear me clearly?
Yes, Kosuke.
Okay, so shall we start? So today, okay, I'm talking about my recent progress about quantum dispersion calculation. Although I have already mentioned a bit day 3 or day 2. Okay, but in detail, okay, I explain. I'm talking about the implementation and so on in detail, more in detail. Okay, so photon calculations actually based on the valency forces, it's very important. Actually, photon calculations in general play important roles in material science. For example, for predicting for crystal stability, for discussing the crystal let's see, phase stability. So for example, if we see the negative frequency in photon dispersion calculation, it means that the system is not stable, dynamically stable. Okay, so for calculating forces, essentially we need the dynamic matrix. Indeed, the second derivatives of the energies with respect to atomic positions. Okay, so actually so far, my recent progress is not the first example for calculating a phonon based on VMC forces. So let's say, so actually there are several attempts have been done for open systems molecules based on force calculations. Okay, actually to evaluate there is several strategies to evaluate by dynamic matrix. The first one is fitting a potential energy surface with the directly fitting a potential energy surface. Okay, so this has been already reported by our TurboRVB group by Vandrazen and Yellow for calculating vibrational frequencies of waters. Okay, And also there another strategy. There is another strategy, is direct evaluation of dynamic matrix. Okay, direct evaluation of the second derivatives by Quantum Monte Carlo. Actually, this has been reported very recently, actually by other groups using Casino, not TurboRVB, but this was successful for evaluating molecules. I think several molecules have been evaluated by this method, okay, but not reported for periodic systems, okay. And actually did another method, that finite difference method, okay. This can be evaluated by, let's say, using forces, okay. The forces divided by the displacement. We can evaluate dynamic matrix, right? So in TurboRVB, we have so far implemented the strategy, okay, the first one and sorry, the 0 and index 0 and index 2, okay. Unfortunately, the strategy 0, this one, fitting a potential energy surface, is not feasible for essentially for periodic cases, because you know, to evaluate the second derivative of the energies for solid systems, okay, we cannot evaluate all the finite difference. Let's say it's very difficult to fit a potential energy surface for a solid system. Okay, so we in the recent calculation, we employed this finite difference method for the diameter calculation. And actually, after calculating the forces of the system where only one atom was displaced to x direction, is enough for calculating phonon dispersion for the diameter, because thanks to the symmetry. Okay, after calculating the forces of the atoms, we used the phonon P, okay, for the diameter phonon calculation, which was developed by Professor Togo and Tanaka, okay, in Japan, Kyoto University. Okay, so, and as I told you, we recently found that for periodic system calculation, force calculations in periodic systems, how to choose the choice of basis set is so important, very important to decrease the error bars of the forces. Okay, so as I told you the day before yesterday, unfortunately, provided basis set for open systems redundant for periodic cases. So, for example, we can, for open system, we typically use the provided basis as it is, provided basis set as it is. But for periodic boundary condition calculations, typically we should cut exponents smaller than 1.0 typically. Okay, this is also true for periodic all electron calculations. Okay, so for example, one of the very famous database is this basis set exchange. You can visit this website, but usually they are always redundant for periodic case. So it is better to cut the smaller exponents, okay, in quantum Monte Carlo calculation. So actually, this graph I have already shown maybe the day before yesterday. So, but let me explain again. So this is energy, and this is condition number of the overlap matrix. Okay, the condition number of overlap matrix means indicates the redundancy of the basis set. Okay, if the condition number, this is inversion. So this is inverse of the condition number. So here in the here it means that, okay, the basis set is totally redundant. Okay, here in this direction, it means that, okay, the basis set is not redundant, linear independent. Okay, so if for the energy evaluation, actually the condition number is not so important as force evaluations. You can see here the error bars are almost constant, right? Regardless of the value of the inverse of the condition number. But in force evaluations, this plays a very important role. here. So blue ones show the error bars of the forces, okay? As the condition number, the inverse of condition number increases. So let's say the basis set becomes independent. The error bars error significantly decreases, right? So it means that, okay, we should use, of course, we should use independent, the linear independent basis set for calculating forces. Actually, this also affects the values of forces, right? As shown here, the red ones show red points show forces, okay, referring this left axis. So it means that, okay, here the green one is all electron forces, okay. Sorry, all oh yes, okay. And so here in this region, you can see the force is completely okay off right, from the correct one, right? So yeah, we recently found this basis set choice is very important for calculating forces for periodic systems cases. Okay, so in open system, there's no such problem. So because the basis set provided by the database is not redundant for open system, so you can see the in TurboRVB you can check the condition number from the prep output. So you can look for. The keyword is condition number. Yes, the condition, the prep X provides us the condition number. So you can see the redundancy of the basis set after your DFT calculation in TurboRVB. Okay. And
Kozuke, sorry if I'm interrupting you. There is a question on the chat.
Okay, sure.
I don't know if you can read it. If not, Samuel, you can just unmute yourself and ask the question to Kozuke. If you want.
Oh, okay, sure. Oh, let me see. Could you some comment on the difference with the harmonic density function perturbation theory, which results in perfect agreement with the neutron scattering for simple crystalline phonon dispersion or stochastic circumstances? Harmonic approximation for more complicated one. Let me see. Okay, so sorry. Can I reply to the second question first? Okay, so why is there no dependence of all electron force on the condition? Oh, sorry. This reference was calculated by the crystal 90 basis, which is whose let's say the condition number is always good because crystal 19 DFT code, you know, the employed crystal basis, and in which they have already optimized the exponent for periodic boundary condition calculation, suitable for periodic boundary condition calculation. Sorry. Is it clear? Is it clear for you? Okay, so the basis set is perfect. That was perfect. Okay, so the first question. Somebody comment. I should mute.
Well, the simple answer is that this is a problem of DFT. I mean, this is, I don't, so if you are questioning about two methods used in DFT, the only thing that we are doing, density functional perturbation theory allows to compute phonons without using this finite difference of the forces, right? This cannot be done yet in TurboRVB. Well, first reason, because we have to code it. The second derivatives are tough. And the second reason is that we do not expect to have improvement because the forces already contains, we have, by calculating the forces, we are exploiting also already the Quantum Monte Carlo reduction of error bar due to correlated sampling. No, basically forces, we are doing the calculation of the difference of two energy when we change a little bit the positions. And if you go to second derivative, this is possible, it's much cumbersome analytically, but you get much larger variance in the sense that it became more convenient to compute difference between forces with large enough step rather than computing directing the Hessian, the second derivative. So that's why we follow this path in Monte Carlo.
And so for the long range,
the extra
interaction
of to fight with error bars. Second derivative much more noisily. If you compute it exactly, you do a lot of effort, and you cannot do the Hessian of system large like we did with reasonable error bar. Though it's possible in principle. No? I don't know if I answered this question. Probably not, because, but I mean, at least vaguely.
Can you hear me? Can you hear me? Yeah. So, and can you also maybe? So, how do you deal with the long-range interaction? So the dipoles. Let's say alloteo splitting and those things. Do you do the standard? You remove the long range and then you analytically add it. I mean, do you do a Fourier interpolation? Is the question?
Oh, sorry, I could not hear you. So would you give me your question again?
Can you hear me?
Yes, I can hear you.
So in order to treat the long-range dipole or quadrupole interaction, so in the long wavelength limit, as you approach Q equal gamma, I guess you cannot treat this with finite difference. So do you do a Fourier interpolation and add this analytically?
Oh, Fourier interpolation.
Of course, in diamond, it's not an issue, but if you do,
yeah.
But if you do any other material, let's say that are polar, which is almost all material, if you do gallium arsenide, how would you do that?
Oh, sorry, I cannot understand. So, so I mean you're wrong in so of course there is long range interaction between among atoms, right? So your question is how to treat the long range forces in this method.
Yes, that's the question. So in the case, because of course in diamond it's okay, but can you use your method for gallium arsenide? Bulk, crystalline gallium arsenide.
In the finite difference method, maybe so we calculate the forces of the supercell, right? So by increasing the number of supercell, it is possible, right? We can consider also consider the long range interaction taken into account, right? Consider the long range interaction into account, right? I think so. I believe so. But the problem that QMC, for the diamond, I use the 2x2x2, just very small calculation, small supercell size. But in principle, it is. Sorry, how can I answer? So I think we can consider also the long range interaction by increasing the number of supercell size.
But you would need an extremely large one.
Yeah, extremely large one. Yes, extremely large one. So this is actually this is a problem. This is one of the drawbacks in my approach. So if the long range interaction is very important, I don't think we can within the reasonable computational time we cannot. Within the reasonable computation time, we cannot calculate the phonon dispersion calculation taking in the long range interaction into consideration.
I see. Thank you.
Yeah. Right. That makes sense. Okay. So proceed. So, sorry, I forgot to tell you. So to evaluate forces with the finite difference, finite variance, one strategy is that to cut smaller bases, small exponent, right? But in TurboRVB, there is another option. There is another option, which is IPS over. Okay, IPS over. If IPS over is switched on, turned on. For example, IPS over. If you put IPS over equal 10 to the minus 7, the TurboRVB prep automatically cuts the basis set such that the condition number becomes 10 to the minus 7. Okay, IPS over. This is a very important option when calculating forces of periodic systems in DFT. Okay, this and we have recently as I told you, the forces are evaluated by the algorithmic differentiation method, right, in TurboRVB. Okay, it implicitly assumes that the correlated sampling works well for when evaluating forces. Okay, so so this method assumes that the wave function does not change much, even when the atom is displaced. Okay, the correlated sampling works only if two wave functions are close, very close enough. Okay, so we recently found that we confirmed that the linear dependency of the basis set deteriorated the overlap. If the basis set is very ill-conditioned, the overlap matrix becomes far from unity. Okay, so actually, when I calculated the overlap matrix by displacing atom by hand by 0.005 Bohr, if the basis set is well conditioned, the matrix, the overlap is 1. Actually, completely the overlap. Okay, overlap was perfect, but when the basis is ill-conditioned, the overlap was deteriorated. We have confirmed also by checking directly calculating this overlap. Okay. Let me see. So this one, and okay, and if someone is interested in the force calculation for TurboRVB, I strongly recommend you should check the consistency between potential energy surface with the forces calculated by, directly calculated by the quantum VMC. Because as I told you, there are additional terms in quantum Monte Carlo calculation. So this condition is not, okay, when it, as far as you optimize the variation parameters of the determinant part and as well as the Dastor part at the JHP level, the condition is satisfied. It means that these terms vanish. Okay, so in that case, in this case, the forces obtained by the obtained forces should be consistent with the potential energy surface. But at the JSD level, we do not optimize the molecular orbital coefficient. So it means that these additional, we are not sure if these additional terms play some role in actually the significant or not. Okay, so you should check for example, for let me see. So even for the periodic systems, we can define potential energy surface, right, by displacing atoms according to, for example, along some photon vibration. Okay. So this figure shows, okay, this is quantum space calculation of diamond, and this is the corresponding one done by TurboRVB. Okay, and blue points show the potential, the energies along to the displacement of the atoms. Okay, and also this one. And red one is red solid point show the forces calculated by the forces obtained by the direct calculation of the forces. Okay, and the broken red line shows the potential, the derivative of the forces, derivative of the potential energy surface obtained by obtained from this, potential energy surface. Okay, so they are consistent, right? Completely consistent at the DFT level. This should be, because DFT, at the DFT calculation, there is no additional term for the forces evaluation. So as I told you, so there are no such terms in DFT calculation, okay? So, but on the other hand, so at the VMC, at the VMC calculation, in the Quantum Monte Carlo calculation, they are not 100, we are not 100% sure they are consistent at the DFT level. So every time you calculate forces for the periodic systems, it is better to check the consistency before, for example, you calculate for phonons, okay? Is it clear? Okay. And recently we calculated the phonon dispersion diamond, okay, using the conventional 2x2x2 cell with the experimental lattice parameter. Okay, I used the experimental lattice parameter instead of optimizing the lattice parameter, the stress, okay, the crystal cell, okay. And as I told you, the frozen method implemented in platform phonopy package was used for calculating forces. Okay, as a result, they obtained, for example, here the orange lines our results, okay, based on phonon VMC forces, and black ones the experimental result. Okay, they're let's say, yeah, consistent with the error bars. Okay, fortunately. So, and here I showed several Raman frequencies, let's say optical phonon at gamma point, the highest optical, highest frequencies at the gamma point. DFT LDA gives us 38.55 terahertz with the experimental lattice parameter, but our VMC calculation gives let's say a much more accurate result, closer to the experimental value. Okay, they're harmonic frequencies. Okay, so experimental one is, of course, experimental frequency includes anharmonic effect. So we subtracted the anharmonic effect estimated by the molecular dynamics simulation performed by Tommaso and Michele, okay, in this paper. But actually, there is one open question is still there. When calculating the equation state, I mean the energies with respect to volume per carbon atom. Okay, the black dot line shows the experimental equilibrium volume. Without, okay, we have already subtracted the 0-point energy, okay, from the experimental, because the experimental lattice parameter, of course, includes the 0-point effect. So subtracted that, okay, here. But even at the LLDMC level, so our calculation is this one, the purple one. Let's say the equilibrium volume is not far from the experimental one, but there is still small discrepancy between our DMC calculation and the experimental value. And 2003, maybe 10 years ago, Professor Maezono has also calculated this equation state at the DMC level, and he obtained this solid purple line. Okay, this is a bit. This DMC gives us a bit larger, larger volume, equilibrium volume compared with the experimental one. On the other hand, our DMC calculation showed us a bit, smaller volume compared with the experimental one. we think the Professor Maezono and us we actually started from different nodal surfaces. Professor Maezono started from the PBE node, okay, GGA node. On the other hand, we started from LDA node. So this is why the two curves are not consistent in our opinion. But actually, this is still open question. We guess that we guess this discrepancy comes from the nodal surface error. So in the near future, if it is possible to optimize the nodal surface for this diamond, we believe this that could solve the discrepancy at the LDMC level. But this is still open question. Okay. So okay, let me. But okay, so the phonon calculation, if you are interested in the phonon calculation based on the VMC forces, of course you can calculate using TurboRVB. But there are several limitations, and we should know this one. Okay, so the phonon dispersion calculation has been already implemented in TurboGenius, but this is now under refactoring. So once I finish refactoring, I'll tell you on the Slack channel. Okay, and the other problem that. Another problem that, for example, it is not semiconductors with more than 2 elements case is problematic because we cannot include the LTO splitting effect. So to include the LTO splitting effect at gamma point, we should calculate the Born effect, Born charges, right? To compensate the effect. But unfortunately, at the VMC level, we cannot calculate this one. So if you need, so maybe one possibility that you calculate this LOTO splitting using DFT calculation. This can be correct because plus DFT, you can use DFT correction. You can add DFT correction to our VMC forces. This is possible, but we cannot estimate LOTO splitting, unfortunately, at the VMC level. Okay, and also we should be careful about the compounds that have the degree of freedoms in their atomic position, the Wyckoff positions. I mean, for diamond, all the so all the atoms on the high symmetry position, okay? So there's no degree of freedom in that sense. But for example, for general case, for example, for let's say, so gallium arsenide, okay? We should search for equilibrium positions, okay, at the LDMC level before a phonon calculation, okay? So, but unfortunately, VMC and DMC, of course, QMC calculations have some noise. So, but it's a bit difficult to find equilibrium positions at the VMC level. So we should be careful about that too, if you are interested in the phonon calculation of compound, okay, that have the degree of freedoms in the atomic positions. Okay. Another one is okay. The anharmonic effect is not taken into consideration at present. To consider the anharmonic effect, of course, within the finite difference framework, it is possible to consider the anharmonic effect, but we need much more displacement patterns to include this one. So, and also, yeah, another implementation is needed, but that has not been done in TurboGenius. So maybe in the near future we will do this, and once we implement this one, we will now announce it on the Slack channel. Okay, actually that's done. So thank.
A question in the chat.
Sorry,
there was a question by Ivan.
Okay,
Yeah.
so okay, thank you very much. So okay, how much will the results of phonon calculations change when you use the smaller QMC volume instead of the experimental volume? Oh, this is a good question. To be honest, we have not done this one. So I've just done the phonon calculation at the equilibrium position. So yeah, it is very interesting because I assume that. Oh, sorry. Okay. In this paper, we concluded that our you know, our phonon dispersion, this VMC value is accurate, even though we, for example, we changed the parameter, because let's see. So from okay, in this paper we estimated the change in the Raman frequencies by the DFT LDA calculation. So I mean that the change in the frequencies should is consistent between the is almost, let's say, equivalent between LDA and VMC calculation. So in principle, it is so let's say, so we have not confirmed that our assumption is correct or not. So this would be very nice future work. Yeah, thank you very much. Makes sense.
We launch a poll where there are 10 questions in order to get the certificate of the school. So I will leave just 2 minutes more. If you have any question, just unmute yourself and ask the professors, or just paste your question in the chat.
And so we have a Q&A session.
So there are, this is the time to conclude, or?
Yes.
Of course, yes, I will take the honor to conclude, not because I'm more important, but because I'm older, and probably older in all the group that we are. I thank you very much for being here until the end of the workshop, of the school, and I would like to say that it was unfortunate that we could not have this school in person, and we suffered a little because we cannot see your face during the lecture, and we don't understand well what is the reaction. But at the end, thanks to the Trust IT, they prepared a very nice poll, no, right, that you should answer, and we will see whether what is your feedback and what you have learned, if you have learned something with this school. I hope most of you enjoyed. I have to say that what you miss without being in person, the beautiful city of Trieste. I hope the next few years you will come in the summer, a beautiful beach, and you can enjoy. Again, I remind you, if some of you want to download the TurboRVB code, you have to prepare, you have to have an account in GitHub, and you have to sign in the CISA GitHub. So just Google CISA GitHub, and there will be sign in, and you put your username there. When you have registered in this link, then you just send us an email, because we have to do a further operation. We have to include you to the project. So you don't have to worry if you enter and you don't find TurboRVB, because we have to include you in TurboRVB project. What else I have to say? Well, I think I was very proud that since Monte Carlo is something that is done by few people so far, as compared to density functional community that is couple of order of magnitude larger than ours. And nevertheless, this school received several applications, and you are here still without many, despite the fact that this is an online school and it's very easy to go away and do another thing. So I'm very happy that this was successful. And I thank you, and I hope that the next we will have the occasion to meet again in a couple of years, or maybe next year there will be another school of Monte Carlo with another code, I suppose, under the TREX support. And so stay tuned, and we will, I hope we will continue to interact with the Slack channel and by email at least, you know. And I hope to see you again in some way, in person, right?
There are questions going on. Should we get the answers or not? We can, could you ask Julie? The questions we proposed.
About the question, they are...
The pool. Should we wait for the pool or not?
Yes, we will keep it open. So we encourage everyone to answer the poll question. We'll give you until 10 minutes more. Then we could also share this via email on our thank you message later, so that you could answer it and then provide it to us.
Yes, we need 10 minutes. And then we will put after some day the answer. Yeah. Well, actually, there are another thing that I want to say, that since TurboRVB should certainly became a free software, no? So not private, in 2023. So we we will put in Turbo RVB web page. If you Google TurboRVB, we have our web page, and if you want, there is the possibility. We will put the possibility to download the code after one fill in a simple form. We need to know your. So if you forget, if you in some period you want, you believe that you want to use TurboRVB, not necessarily now, you can do in a couple of months, no problem. Okay, let's go. No, you have to say something.
Q&A session.
So if there are questions, we are glad to answer now. But there were several questions in your.
Actually, yes, one of my students asked me yesterday in the tutor session, okay, the PrEP DFT, there are two DFT energies. One is final variation DFT energy, and one is final self-consistent DFT energy.
Oh, that's a very nice question. Yes, you know that density functional theory is variational in the sense that you have a functional that have to be minimized. And for instance, you get better energy functional with the same functional if you increase the dimension of the basis set. But in order to compute in the self-consistent approach, you don't compute, given the density, you should have a value of the variational energy. So that has to be minimized. So if you are out of the minimum, this is larger. But during the self-consistent, it is more simple to compute, at least in Turbo this is done. Some of you noticed that, for instance, Quantum Espresso, you have always the variational energy and not the self-consistent one. But if you compute the energy during the self-consistent cycle, it's more convenient to assume that you are at self-consistent and the density is consistent with the eigenvalue equation that you are solving. This is not the case, it's done only at self-consistency. So only at the end, in order to save some computational time, I compute the variational, the true variational energy, in the sense that if the calculation is not converged, you should find a better value by iterating more, or if you have a larger basis. Usually the two they are exactly the same, because it's also a check that you arrived at self-consistency, so that's why.
So if there is some difference.
So if there is some difference, it means that you are not at the correct self-consistent.
And the other question.
Yeah.
Well, my students ask me, what is the new lowest eigenvalue in the range simplification? During optimization, we can see new lowest eigenvalue.
Ah, this is a regularization. I mean, I've seen Kosuke that did a wonderful job for this hands-on. Has prepared very tough. So he has defined a variational wave function with several parameters. And of course, there is some problem when you apply the linear method with so many parameters. There are, in some cases, too much redundant direction. And so that in the linear method, actually he used a very special, but unfortunately we have not explained, maybe next time we. So somehow you try to do, to define several directions of optimization. And for this selected number of directions, one of them includes the stochastic reconfiguration direction, which is s to the -1 applied to the forces. But there are also in this data input that you have further 10 directions that are determined by the variational parameter that have maximum signal noise ratio. Then when you do the linear method, you discover that you have too much, I diagonalize in this case the overlap matrix in this 10 or 20 direction, and I discovered that there is some too much redundant direction, and so what the code does is diagonalize this matrix, because this is small, 10 by 10, does not take, is not 20,000 by 20,000. And you remove, you do an iterative algorithm to remove from these 10 variational parameter the most redundant one. No? And then after removing, we check if the new eigenvalue is larger than the fixed threshold. The fixed threshold is defined by convention by your value that you have put, this par r that you have put. This was 10 to the minus 1, I think, 10 to the minus 2. And if it is happy, so it finishes to eliminate direction until the lowest eigenvalue in this overlap matrix is larger than this, so that you can do a stable optimization. So this is very, 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 so you should not see this if you use the standard. Actually, I modified the code with my students and I use the standard stochastic reconfiguration, I do only one direction and I don't care. Okay, I hope it is a technical detail that you can avoid if you want.
Anything else?
So we should make some applause for all. Right?
Yes, if you want to add additional remarks coming from our key speaker, Michele and Kosuke, feel free to say it before we close the session.
Oh, oh sure. Okay, so okay, so thank you for joining our school. So as I told you, we have already created the Slack channel, right? So if you have some questions about TurboRVB, how to use TurboRVB or how to download or how to compile, etc. So please feel free to post it, or of course direct message are also appreciated. So to Sandro, to Michele, to me, so would you send us a message, okay, on the Slack or via email. Okay, that's all. So thank you very much.
Thank you.
Thank you. And Michele, do you want to also say something, or if not?
How long?
Time for question. I see there's still a lot of interest. You might, but I think questions offline, I mean, can always be asked. So we have different channels, as Kosuke said. So the Slack channel, or we have plenty of ways to get in touch with us, even through the website. So this is the first school that TREX organized. So there will be more in the upcoming 2 years. Let's see if we manage to have them physical again. And we'll have a training section on our website soon, where we hope you'll find also useful materials. And then I really thank you. I saw you were very active and very engaged. A special thanks to all the tutors you had, but really, again, a special thanks to you for the interest you showed. Keep in touch with the TREX project, because more releases and updates will come in the next months. And thanks, I see thank you messages coming in the chat. So it's very rewarding. We'll probably get in touch with few of you who can help us providing some testimonials, some lessons learned about the schools. So you'll receive some messages from us. And feel free to share the experience on your channels, on your network as well. And that will help us all. I think that's all from our side. We see that people are also filling in the poll. Thanks. And unless, Michele, you want to officially close this, I think we can free everybody up now after this very intense week. Okay. So thank you all. Enjoy the weekend and enjoy the summer ahead. Thank you all. Bye.
Thanks.
Bye-bye.
Bye-bye.
Bye. Bye-bye.
Okay, now we shall leave. Should leave, right?
Yeah, or if you want to stay just to
So Jacopo and Sarah,